So what we're going to do here is I want to look at geometric representations of complex sets of numbers. So this is going to take the Argand diagram, which is a geometric representation of a single complex number, and extend this into sets of multiple solutions of complex numbers themselves. Now, the reason that we're going to do this is that it can have interesting geometric interpretations involving these sets of numbers because they have to satisfy certain restrictions and values. So for example, the solutions of an equation can lie in a circle or a straight line depending on the restrictions imposed and the type of complex number we're looking at. Let's start by considering the equation modulus z equals 1 and ask ourselves what solutions satisfy this equation. So what complex numbers satisfy this? Now we know modulus z represents the length of what we would call a vector from the origin of a complex plane to a point P itself. What we know from this is that the length of that is 1. Now what this means is that we can have multiple solutions to this depending on where we place z within the Argand diagram. We could have any number of solutions as long as it is a distance of 1 away from the centre, because that is the only restriction we have placed on this complex number. So if we look at this Argand diagram here, there would be my centre. Every single point on this red circle here is a distance of 1 away from that centre. So each of them represents a complex number where the modulus of that complex number z is 1. So we can represent that by a circle, which is great. We can use this, and it's quite nice to be able to think to ourselves, well, I can represent a set of solutions in a circular pattern or a circular shape. But it does raise one key question. If I can do that, how do I determine the equation of this circle? So it's nice to know I can do it. Great, I can get a wee cheeky circle. But how do I get the equation to that circle? What do I have to do in order to calculate the equation of that circle and be able to then use it to further the understanding and the mathematics we're going to be working with? Well, let's stick with the simple example we talked about there. Let's consider modulus of z equals 1. Now remember, our standard format for z, our complex number, we said was x plus iy. And we said modulus of z was equal to square root of x squared, so the real part squared, plus the imaginary part squared, y squared. So what this means here is modulus of z equals 1 literally means that I can say that the square root of x squared plus y squared equals 1. Now if I square both sides to get rid of the square root, what I can then say from that is that x squared plus y squared equals 1. So what this is telling me is that there is the equation of a circle who's got a centre at the origin with a radius of 1. So all my solutions within the set of complex numbers I'm going to consider where the modulus of z equals 1 are represented by that circle. I could pick any answer on that circle and I would get exactly what I want. I could pick a specific one depending on any further conditions I impose, but with this condition of modulus of z equals 1, that's what I've got. Now in this case we said modulus of z equals 1. How does that change though if we were to rewrite it as modulus of z is less than 1 or modulus of z is bigger than 1? Well, same logic as I've got here, but if I did modulus of z is less than 1, what I'd be saying is that x squared plus y squared is less than 1. Now I would still have the circle of radius 1. So I'd still have my circle of radius 1 in my imaginary and my real plane. However, what I'm telling you here is that x squared plus y squared is less than 1. So the modulus of the vector represented by the complex point z has to be less than 1. So what that means is I can say any solution to the modulus of z is less than 1 is given by any point within this circle here. So the circle where x squared plus y squared equals 1, so centre at the origin with a radius of 1. I can use similar thought processes and logic when I've got modulus of z is bigger than 1. If I have modulus of z is bigger than 1, what I'm telling you is that x squared plus y squared is bigger than 1. So if I again think of the same scenario, I've got the same circle from before, my circle here, centre at the origin, radius of 1. If I'm telling you I want the solutions for x squared plus y squared is bigger than 1, that's everything outside the circle, because the modulus of my complex number is larger than 1, so it lies out with the circle. So anything that satisfies x squared plus y squared is bigger than 1 gives me a solution anywhere beyond the circle. So we can geometrically represent something written in that format as a circle. However, looking at that, modulus of z equals 1 is great. That's a circle with a centre at the origin. We know, though, circles can have a centre anywhere within our plane. So how do we work when that happens? Well, let's consider modulus of z minus 2 is equal to 3. And we want to ask ourselves how it will affect our calculation. Well, if we previously think of the fact that we had modulus of z equals r representing the radius of the circle, what we're going to do is imagine that we are writing it as modulus of z minus w equals r. What this is asking us to do is find the distance between two complex numbers z and w on the Argand diagram with a distance r. So you can imagine I've got my complex plane there, I've got a number there, z, so my complex coordinate there, and I've got another one, let's say it's w there, and that there is the distance between them. So it's the distance between those two complex numbers. And if I were to look at it like this, so my modulus of z minus 2 equals 3, this is going to do the same sort of thing, represent a circle, but this time my centre isn't going to be at the origin. We're going to have moved the centre. It's going to affect our calculation in that manner. So let's have a think about this. Well, modulus of z minus 2 would be the equivalent of me saying it's the modulus of x plus iy take away 2 equal to 3. Well, if I group the real and imaginary parts here, I end up with the modulus of x minus 2 plus iy equals 3. And if I then calculate the modulus, so square the real, square the imaginary parts, what I get is square root of x minus 2 squared plus y squared equals 3. And again, getting rid of the square root by squaring both sides, what that tells me is that I've got x minus 2 squared plus y squared equals 9. So there you go. In this case, what I'm telling you is that I've got a circle, my radius, square root of this side is 3, but my centre is no longer at the origin. For this sort of equation here, think back to when we did the equation of a circle, my centre C is going to be at the point 2, 0. So it would look something along the lines of that. So I've got a circle here, my radius there is 3, and that there is my centre, and the coordinate of that centre is 2, 0. So we can change the interpretation in terms of circles by just manoeuvring the centre and shifting it a bit. But there have to be other types of interpretation as well. One that we're going to consider here is straight line representations in the same geometric fashion. Now these will take this format here. Magnitude of z minus a equals a magnitude of z minus b. So let's consider, we'll stick some values in. We're going to look at magnitude of z minus 3 equals the magnitude of z minus 4i. Now what this is going to represent is the distance from the two centres, so the 2 points 3, 0 and 0, 4 to z. Now that means that z needs to be the same distance from both points. So essentially, z is the centre of the distance between those 2 points, and it's going to have to lie on the perpendicular bisector of the line between these two centres. Now, it's a lot of information to throw at you. The best way to think of it is looking at this diagram here. What we want is the middle of the distance between the two of them. So if we were to take a line going from A to B, and then find the perpendicular bisector to it, so it's cut it directly in the middle, this is the same distance as that, what I could then do is if I were to find any point on here, it would be the same distance between A and B, and that would be the representation that we are going to get there. So we would get the equation of this line here and that would represent the set of solutions within the complex set of numbers that we would be after. Now, it's easily illustrated in an example, so let's stick with what we did here. So let's stick magnitude of z minus 3 equals magnitude of z minus 4i. So put the values in. We're after modulus of x plus iy, take away 3, equals the modulus of x plus iy, take away 4i. What I then do is group the real and imaginary parts of both together as well. So this one, I'm going to have x minus 3 plus iy equals modulus of x, and then I'm going to group the imaginary parts together, plus I bracket y minus 4. Square both sides. What I can understand with this though is that if you remember it's going to be square root of x squared plus y squared in terms of our standard format, they both have square roots. So let's focus on what's under the square root and ignore that. So I'm able to then say that because of that, x minus 3 squared plus y squared equals x squared plus y minus 4 squared. So we've got all of this on both sides. That involves a lot of information there, and you're thinking to yourself, well, straight line equations don't involve squares. Well, when we multiply out these brackets and start to simplify it and get it in the format we want, the squared terms will disappear. If I multiply out on this side, what I'll end up getting is x squared minus 6x plus 9 plus the y squared. That's going to equal x squared plus y squared minus 8y plus 16. So I've got an x squared on both sides, they go, and I've got a y squared on both sides, they'll go, and then I've got the equation of a straight line. So what I can do is stick it all on the one side. What I'll end up getting is 6x minus 8y, I've then got 16 take away 9, plus 7 equals 0. That there represents the straight line that I'm after. So the straight line that provides the solution to this set of equations in the complex plane. Now if we were to rewrite it, so take all the y's across and write it as 8y minus 6x minus 7 equals 0, that would still be the same equation of the line. We'd have just written it essentially back to front. And if we really wanted to be smart and write it in the format of y equals mx plus c, what we'd have is we get y equals 3 over 8x plus 7 over 8. And that would be the format there. Now we tend to stick with the first two sort of format, so standard equation of a straight line. This may be asked for. Any of the three formats are fine in a general question. Just watch for it asking in a set format. And that's how we'd solve this one here, and how we'd work this one through. That's how we'd find the equation of that line that provides a set of solutions, i.e. the set of complex numbers that solve this equation here. So thinking of it, there's a few set formats and we can instantly look at them and say, right, this is the kind of shape it's going to represent, or this is a set of numbers that are going to satisfy the equation I want. If we have something written as the modulus of z equals r, that's going to be a circle with a radius of r and a centre at 0, 0. If we've got modulus of z minus a equals r, that's a circle of radius r, but it's got a centre at a in the complex plane, so we've shifted the centre slightly. Now for any of these ones, so this includes the magnitude of z as well as magnitude of z minus a, if we have less than r, so it's a set of points within the circle, and if we have bigger than r, it's a set of points outside the circle in the complex plane. So we covered that in the previous example. And then the last one was the last example we looked at, where we had the modulus of z minus a equals the modulus of z minus b. What that was that was a set of points lying on the perpendicular bisector of the line from a to b. That represented the solutions to the set of numbers of the complex in the complex plane for that. So we have to bear that in mind when we're looking for these sorts of solutions. We're no longer looking for a single answer like in the Argand diagram. This one here has multiple answers. It's got a full set of solutions represented within the complex plane, a complex set of numbers.